Thank you very much, Matteo. Is it okay? First of all, yes. Can people hear me from outside? Good. Yes, so thank you very much, Massimo, and thanks to the other organizers for having me here. Always a pleasure to be in Trento and to participate in this very nice series of workshops. Now, just on the bus, I realized that I didn't put the title. I tried to think of some clever joke to justify this, but I mean, I just forgot. So, but I want to talk about the fast crossover. The title was Fast Crossover in QCD and its relation with the scaling window of the theory. So that's issues and questions are just outlined here. And so we wonder, so we know that the quark-gluon plasma right after the critical temperature is very much strongly coupled. And we know that eventually we will have to end up with a weakly coupled theory. But then we ask the question how this happens. Does it happen gradually? At which range of interesting temperatures and so on and so forth? And I want to say as a theorist, this is a nice question. And I really think it's purely theoretical because I'm not sure the experiments would really be able to assess where this threshold exactly is. They can see the plasma is strongly coupled. This has been seen clearly in experiment, for instance, from transport properties and whatnot, but really to have this fine control and to check how the transition to it. So this is for us to do, so it's a nice problem. And then of course, some colleagues went as far, some of them in the audience, as to propose that this is really a true new phase, indeed, maybe with its own order parameters and distinct symmetries. It's a very fascinating hypothesis, these are ones. And then staying close to the topic of the workshop. So the question is, how is topology being used in this setup? And also how all this connect with the known criticalities in the phase diagram for real or in general for complex parameters setting. And then also Francesco gave a very nice talk yesterday and brought to my mind these pictures. And then of course, this discussion on the Roberts-Weiss critical point. And indeed, so this is a sketch of phase diagram in the mu square temperature plane. So we know it has been discussed very much that there is an endpoint of a first order line. Being a first order line, this is a genuine critical point, which has been much investigated. And what one can see, for instance, if I sit exactly at the temperature of this Roberts-Weiss endpoint, all the thermodynamics, so for instance, the number density follows power law scaling. So with this alpha, which is not an integer number and not just a simple real number, it's just a critical exponent. And then clearly this somehow rules out any simple behavior which would be approached only for very high temperatures. And then clearly then wherever we approach criticalities, strong interactions may be into play. And already from this very simple argument, we know that the quark-gluon plasma cannot be weakly coupled for temperatures which are below the Roberts-Weiss endpoint. That we has been estimated, most recent estimated places this point slightly above 200 MeV for the physical case. So I would say this already tells us that the quark-gluon plasma should remain strongly coupled at least up to this temperature. So in general, this brings question, how is this singularity send the message that they are there and how do they influence the system? So this is a phase diagram which highlights genuine critical points that this has been, I think the plot has been done by Fritjof already a couple of years ago. So this is a phase diagram in temperature, chemical, baryochemical potential plane, and the light quark masses are indicated. So the physical plane is up here. So here is the pseudo-critical point, the crossover that we measure. This is the critical point in the current limit. The current estimate is about 130 MeV with some discussion attached, which I'll come back later. And this is the tri-critical point searched in experiment. And when we study this critical point here, besides studying the issue of the critical behavior in QCD, we also place, indeed, by reasoning, by some educated guess on the shape, but well-motivated guess on the shape of the critical line, we place a bound on the existence of the critical endpoint, which has a strong experimental significance. So the search for this point, as we know, is motivating experimental programs very much in the US, the major effort at DNL, but also in CERN with new fixed target experiments that are coming up to search for this point. So when we study critical behavior in QCD, indirectly, but also significantly, we give information, also phenomenologically relevant information here. But what interests us now is to understand how the critical region around, how big is the critical region about the chiral critical point of QCD, and whether we ask the question whether this critical region tells us about the extent of the strongly coupled quark-gluon plasma. So is this any relation? Can I make the observation, and then it would be observation, whether indeed the plasma remains strongly coupled within the range where the system is still described by the general properties associated with the existence of a critical point. So that's the simple outline of the talk, what I want to say. Now, what do we know? So, I mean, the observable, as we know, the observable, as we know, that we study, the simplest observable that we access on the lattice to study topologies, the topological susceptibility. So first, momentum of the topology, the fluctuations of the topological charge. So I did steal a slide by Giovanni Villadoro, who gave recently beautiful overview of everything is known from analytic methods at finite temperature for topology. And in particular, what has been highlighted is the behavior. We know the behavior towards zero, and the high temperature behavior, famous paper by Gross Pisarski, where the limiting high temperature at very, very high temperature, we expect that the system becomes dilute instanton gas, leading to prediction for a power law decay with temperature. And this cos theta term, where theta is the theta angle of QCD, we know that theta will be fixed to zero by some mechanism. We tend to believe Peche-Queen if we need that. Carrie here also was telling us that there may be other reasons, but anyway, we have strong experimental evidence that theta is zero, but still the form of the potential in the instanton, dilute instanton gas is this one. And so when we want to know whether we have reached this regime, we also check whether we are in this simple cos theta regime by exploring further higher order fluctuations, as we will see later. So finite temperature, if we want to know a little bit more about finite temperature topology, we have to look back at the papers by Gasser and Leutwiler. So they, at leading order, the topological susceptibility follows the chiral condensate at finite temperature. This is the result. The next to leading, the leading order is constant. Next to leading, this is the result. And we see that results are reasonably stable, about 100, and then of course we lose control. So summarizing, this is what we know. So chiral perturbation theory guides us up to 100 MeV or so. I don't know of any check at finite temperature. It may be a nice and challenging study to follow this. And then at some point we would approach this dilute instanton gas, and the strategy to assess this again is to compare with this behavior, measure this exponent, observe indirectly the cos theta term in the potential by cumulants, basically, but everything in the middle is left to lattice QCD and perhaps holography that I still have not exactly sure what is been exactly done. So I look forward to hearing maybe more. And the question is again, when this behavior sets in. So then the lattice, we heard already beautiful introduction to topology in Claudio on Sayantan. So I certainly won't repeat it. What I will use in this talk is the method I think used first by Sayantan and Peter Petreschi, in which you notice by manipulating Alhia-Zinger theorem this way to estimate the topological susceptibility. And then by proxy, in the symmetric phase, you is enough, you estimate the axial disconnected chiral susceptibility by the simple disconnected part. And that makes the measurements extremely easy. Because in this way, the topological susceptibility is simply measured by the dispersion. It's a simple chiral susceptibility. I must confess now, by listening of the problems of tunneling, I am more and more confused by this equality, because one would conclude that tunneling is not so important to measure the chiral condensate, but then it's so important to measure topological fluctuations. So how do I put together? So I don't know, but at the moment, let me trust this and take also the checks, because Sayantan in his talk has also presented a very detailed check that these methods very well reproduced the fermionic results that are probably the most solid, as also Claudio has explained to us. So we will use this simple-minded, of course it has less lattice artifacts. When I work with gluonic methods, I work with a local operator, and then I have to fight against all this dislocation. That's we know. This is in a sense built on the long distance physics, so it's reasonable. I will show you some continuum extrapolation. But so, what just one word about the lattice setup. You need fermions with good chiral properties. We don't have too expensive, hard to afford. So we find the best compromise by using this twisted mass formulation by our friends in Rome and Berlin. They have developed. And in this setup, these are basically Wilson fermions. So we have a good Dirac spinor not destroyed, but with some trick, they have a better chiral properties. So basically the gallstones follow a simple scaling with the mass. You don't have to once you tune to this maximal twist. And lattice artifacts seem to be well under control. At least this is what they find with excellent set of results at zero temperature. So we have dynamically strange and quark strange and charm at their physical values. So at the temperatures that we are exploring, the charm may become relevant. It may seem surprising because the charm is very heavy, but remember that we have a 2 pi multiplying temperature. So what really you have to compare, I mean, just to as a rule of thumb. So the relevant quantity is 2 pi t. So it's not so strange that charm becomes relevant so early. And this is shown in analytic calculation, a half thermal loop by the Mikolainen, Alexei Porin, and Helsinki group. They have shown this. So it's interesting to have, of course, to have a dynamical charm that comes for free anyway in this approach. So we have a physical strange and charm masses, and up and down, at the beginning we used different masses because we didn't have the physical mass. But in the end, following the behavior with mass is interesting also for the purpose that we are addressing, because we want to see how far we can go in mass to assess, for instance, the effect of the singularities, and following the mass scaling and the scaling with the external fields, because from the perspective of chiral symmetry, just mass is an external field, then this is really what do we have to do. It's very important probe changing the mass. So some notes about statistics, etc. So just to let me jump into results without many details. So I put a collection of these are our results. This is the physical pion mass. For the heavier masses, we were bold, and we did the scale with this prediction by that would be the dilute instanton gas prediction. But if we look at the way indeed this prediction comes also easier from here, because if we use this formula to estimate the topological susceptibility, we have a square of the light quark mass, and then something that in the symmetric phase doesn't depend much on the mass. So it's I would say a naive scaling, which may be appropriate anyway in the symmetric phase, appropriate, moderately appropriate. So the different masses indeed rescaled collapse on approximately single curve. The agreement is not so fantastic, but acceptable with other group. I hope, Massimo, I have now the final, I don't know whether these are the new results, these are the 2018. So this is, we are in decent agreement, probably results are still improving also from the Claudio talk. So we can see how well finally we compare with each other. So as an excuse that there are these variations, but the original motivation to push the results so far in temperature, also coming back to some discussion we started yesterday, was to study the axion mass, and the impact on the bounds on the axion mass are not very sensitive to these errors. So to the continuum limit, we did some, we have a different lattice spacing. We work in a fixed scale approach, meaning that we change temperature by changing the number of points in the time direction, but we repeat this for different spacing. And so by interpolation, we can also reconstruct the other approach in which we fix NT and we change the lattice spacing, we change beta. And so by doing this, we can study the continuum limit in a traditional way by selecting a number of temperatures and following the scaling with the square of the lattice spacing as appropriate for improved action. And then we see that the continuum limit is decent, so this doesn't matter. So now to the question of the approach to the dilute instanton gas behavior. So the simplest way to extract this exponent, rather than in fits, maybe a little bit, a simple visual way is to build this derivative. So if I'm looking for exponential decay, power law decay, then the power is simply extracted in this way, much in the same way as we do effective masses. So it's the same thing. And this is a result that I find a bit curious and also different from other groups. So we find similar results as other group in that we approach the Digger results, say about 300, it's not so sharp. But then apparently we are first above the Digger results, then we go a little bit below, and finally we approach finally from below. But there is a region where this is above. And this is a bit reminiscent of what Edward was finding in 2000, suggesting 2017, that there should be faster decreases preempting the instanton behavior. Then I don't know, honestly, whether this is really mandatory, this different shape, and it would be really good to check better, interesting to check better the results in this region for the purpose of characterizing this area. So this is what we find. And the approach to the dilute instanton gas starts at about 300, 350. So this is the summary of these B parameters. I made a summary from different groups. They are a little bit scattered because in some cases it's been estimated with the fit. But broadly, so the idea is that after this region close to TC that we don't know, but when we start looking at higher temperatures, the approach is indeed from, where is it? From below. And the best results that are, of course, from Zoltan, Glavnov collaborators group, it is indeed approaching very closer and closer to what we expect. remains a bit mysterious, the fact that the prefactor, the dynamical prefactor, is off by a couple of order of magnitudes. There are arguments which have been presented to explain this. We still don't know, but it seems that it approaches very slowly, probably it moves very slowly towards perturbation theory. I'm saying it moves slowly because now it's impossible to see this because so this prefactor here is off, so it must have a hidden temperature dependence, but since we can estimate this exponent with confidence over large interval, it is clearly moving quite slowly with temperature. This also says that the approach, the final approach to the full diagram must be very, very far away. So that's, but at least as far as the power is concerned, this is okay. Oh, thanks. Sorry, I haven't seen the chant, but that's fine.
That is excluding the...
excluding the discussion. Excellent. No, then that's perfect. Thank you. So now concerning the theta dependence, which is hidden behind this, so then we look at the fourth cumulant, and this is the one which would be 0 in a case of a purely Gaussian system, and as a very well-defined value for a cos theta shape of the free energy. And I hear that Claudio and Massimo, they want to measure it again better, but you have all the results in which you have some indication of the approach to, again, to Vega. And similarly, we find the same. So it's very hard to estimate at low temperatures, make, I would say, no sense. But above 300, again, the results for the B2 cluster around the expected value. So all in all, from topology, that's all I have to show. Then 350 is as a threshold, but not a very sharp threshold towards dilutive phantom gas behavior, as seen in the power of the decay and in the shape of the potential. Now I want to take the other side of the problem sort of quickly, and I want to study the behavior, the critical behavior around TC. So this is the phases in the strange charm masses up and down, and we are interested in what happens around this axis. So there won't be any discussion on the chemical potential here. The true singularities, genuine singularities are happening here along this line. These are the Goldstone singularities, and then there is the critical point. I just want to flash the symmetries of QCD, but just to say, how do we select N? So which is the number of flavors that we should consider for this discussion. And obviously we have two choices. So the charm doesn't play any role in chiral dynamics whatsoever. That doesn't get any mass. It goes across chiral transition without any effect. So the game is played by the strange quark. So there are, if I work with massless up and down, the strange acts an interpolator between 2 and 3 flavors. So what do we do? And t equals 0, it doesn't really matter because we just count, because the Goldstone are there all the time until the strange is massive. I have the Goldstone, the 4 Goldstone of 2 flavors, and then the 3 pions of 2 flavors, and then I change only at an f equals 3. But the finite temperature, the behavior really is very much sensitive to the number of flavors, and standard scenario is that the strange mass renormalize the coefficients in the effective potential, the quartic coefficients at some point in the equivalent bosonic model disappears, the sixth becomes relevant, and here we have this endpoint particular. So we expect second order transition, finite temperature transition all over here, although with a different temperature. But if I think of the scaling window, there is an effect of the strange mass that I want to point out, and I don't think it has been studied, and is the following, that when I switch on the light mass, I have a scaling window in the light mass, which starts from this critical point, okay? But then when I am here, in the standard scenario, I have the Z2 endpoint critical line, which ends the zone of the first order transition line. So I have a scaling window around the Z2 critical point. So these two scaling behavior, they clash somehow. And so I don't know in the middle what happens. I think the most likely scenario there would be mean field or anyway something different. But clearly the scaling window of 4 should narrow down when I start competing with the other critical behavior. So this is, I think, what the reason why, I mean, the scaling window is small, and I think it becomes smaller when the strange quark gets smaller. What we find, just anticipating the results, is that our physical point anyway stays within the scaling window rather comfortably with corrections. And we come back to this later. So the tool that one uses to study scaling window very traditionally has been already mentioned, is the magnetic equation of state, in which we study critical behavior away from criticality. And the simplest way, so when I say the scaling window, I'm referring to the region of parameters where I can use this magnetic equation of state. The magnetic equation of state contains a universal critical exponent, but also universal function, which has been beautifully computed in spin models in the past. When there are different strategies to identify the scaling behavior, one is direct comparison with the equation of state. So I take that and compare. One studies the dependence of the pseudocritical temperature on the external mass that one infers from this behavior. And one can also define RG invariant quantities, which do not depend on the breaking field at the critical point. That's other possibility, but everything motivated in this context. Now, there is a significant source of scaling violation and also induced by lattice artifacts that are linear correction in mass to the chiral condensate. So the chiral condensate has its own dependence on the mass, but on top of that, it has by lattice artifacts a linear correction in mass, plus the leading order correction to scaling behavior are still linear correction in mass. So we just decided to get rid of this linear correction by subtracting this quantity. Very trivially, we subtract the derivative and multiply by m. So it's very trivial combination. It's basically a combination of the transverse and longitudinal susceptibility. So playing with this susceptibility is not new, has been done in the past. They, of course, encode the critical behavior. So the reason why we like this subtracted chiral condensate, so other groups have defined the subtracted chiral condensate in many other ways, but this one is useful because we can define the equation of state. So it's directly related, can be directly related with derivative of the ground canonical partition function. So we do have a bona fide equation of state. By knowing the equation of state from the standard equation of state, we derive the equation of state for this quantity as well. And which is the characteristics. So this is a side by side from the standard equation of state, and this again, this subtracted condensate from this equation of state. So it's just sharper. It has a clear encoding of the critical behavior, plus subtracts all the artifacts. So it's a trick, but useful. It peaks, it peaks at closer to the critical point. So this is the position of the peak, which determines then the scaling of the pseudocritical temperature. So, you know, you can define equation of state for different variables, and this subtracted condensate is the one which peaks closer to zero, where should be the true critical behavior. Another interesting fact is the asymptotic behavior. So if I look at the asymptotics of the chiral condensate and just go with exponent gamma, power law, but this one goes really much faster, that allows a more clear combination. So these are just the results. So how can I search for critical point? So trivially, the first thing I can do is to search for the direct scaling at the critical point by dividing this order parameter by the expected scaling external quark to the 1 over delta, and where everything crosses, there is the critical point, when this invariant point, and this peaks this value 138 with error of 2 MeV. The other thing is the direct comparison one can make with the equation of state. Now, the point is that fits are always good if you, so one has to be careful. So what do we do? By comparison, we also then consider the mean field behavior. So eventually you will have to cross to mean field. And when also mean field is equally good, then the significance of the true or for critical behavior becomes very low, because you say, okay, but also mean field is good, everything is good. And this is what happens here. So if I fit the data for large mass, the fits are good, but also the mean field fits are equally good. And also the free parameter, the critical temperature, which enters as a free parameter, becomes very large, so very far away. This is indeed okay, that can be understood, but anyway, it's not the real critical temperature, it is clear. When I go down, if I go down in mass towards the critical, thanks, towards the real critical, towards the physical biomass approaching the true criticality, then there is a tension with the mean field estimate, and the free parameter, which represents the critical temperature in the chiral limit, becomes close to the other estimate. This is the traditional scaling of the critical temperature. I then summarize these results at the end. I want to show also the behavior at high temperatures. So this is a good fit to this form for T smaller than 300 MeV. All the masses are nicely fitted with this highly non-trivial exponent. So especially look at the light biomass. So this is a strange value, and then the fit is really good. So I find this, I might say, right, convincing. Now, when I go above 300 MeV, I try then another thing. I try the trivial scaling predicted by Griffith analyticity. So when we forget about the critical behavior, then observables are simple. The Cara condensate is a simple odd power of the mass. That's it. That's general, and that means that these quantities will scale as m pi to the 6. Again, not very trivial scaling, but this is divided by m pi to the 6, and we see m pi to the 6 scaling very nicely followed above 300 MeV. So again, signaling that above 300 MeV, the critical behavior is no longer there. So it's just trivial. So putting together all our results, this is summarizing what I was quick, but I can go back to details. This is what more or less we find. We find scaling is decent in this range of temperatures and more or less up to physical biomass, not in the sense of a perfect scaling, but in the sense that the results may be well understood by O4 scaling with corrections and have tension with mean field. That's all we say. Then basically this is, let me say before closing, if I still have 1 minute, one speculation, because we have found this very broad threshold consistently. I have given 2 examples about 300 MeV. Where this is 300 MeV may be found, well, point where we found 300 MeV is the Yang-Mills transition. Of course, setting the scale always very tricky. The results, the value of the Yang-Mills transition may well depend on how we set the scaling, but let's trust the scaling set with the string tension, or we see, and this is about 300. And then natural possibility is that there is some resilient Yang-Mills behavior with continuous for heavier quark mass. And so I am in some intermediate region here, in which I see the bona fide continuation of the chiral transition, but higher temperature, I feel some remnant of this. That's a possibility. And I also want to comment as a speculation on this very interesting scenario by Andrei and Ovat, in which they propose infrared phase in QCD, in which you have basically near conformal but strongly coupled behavior. Now, if I now draw the phase diagram in the temperature number of flavor space, and then we have discussed a lot this NF equal 2 and possible connection with NF equal 3, but this goes down all the way down to the conformal window. And But we know that the conformal window is strongly interacting right above the critical number of flavor, whatever they are, and then becomes weakly interacting weakly interacting. You have complicated the code, but I understand, very sophisticated. But you go to weakly interacting conformal slightly before losing asymptotic freedom. So it's sort of very tempting to match this infrared phase with the strongly coupled, to extend to the strongly coupled conformal phase, which may also offer some support for a DSCFT scenario. And then if there is such a sharp transition, perhaps also in NF, we should find some sharp transition between strongly coupled conformal and weakly coupled conformal. That I don't know, but this connection, I think, should really explain this infrared strongly coupled phase. Is very natural. And then with it, I am really finished. I just want to show the number. We have used 3 different scaling strategies and successfully. So they describe well the data, and as a byproduct, they give TC in the chiral limit with a decent agreement within each other, and also with the estimate of the hot QCD group, which only uses the other techniques. Not so. We have found this consistent for temperature below 300 MeV, and we lose memory of criticality above 300 MeV, which is above the Robert-Gervais as expected. So that's all. So we have this indication of this broad crossover, very consistently placed between 200 and 300. At the moment, doesn't seem very sharp, but I think there are interesting scenarios to be discussed to understand more. And so thank you very much.